So, hello, my name is Jakub Kuklis, and today I'm going to present this paper, Data Complexity of Finite Query Entailment in Description Logics with Transitive Roles. Thank you for joining in. So the problem that we're going to tackle is of finite ontology-mediated query answering, which is a variant of OMCA, which has been presented a couple of times already in the conference. And here we are interested in its finite variant, in which we only consider finite models of the knowledge bases. So as input to the problem, we are given a knowledge base K consisting of a T box T and an A box A, where the T box generally holds the domain knowledge and the A box holds the instance knowledge. And we are also given a conjunctive query Q, or a union of conjunctive queries. The problem asks whether Q holds in all finite models of the knowledge base. So the DLs that we are going to work with are extensions of the classic DL ALC. And these extensions, their name suggests what kind of extensions they carry. So the S stands for transitive role declarations, H stands for hierarchy of roles, O stands for nominals, I stands for inverse roles, and F stands for functional role declarations. So the results known before my paper are that, first of all, in DLs with transitive role declarations, finite ontology-mediated query answering is not the same as OMCA. That's why it is something worth studying. And FOMCA is undecidable for the DL SHOIF, but has been recently proved to be 2x time complete with respect to combined complexity for SOI, SOF, and SIF in this paper by the authors visible on the slide. And my paper can be seen as a continuation of their work. I use similar methods to establish the data complexity of FOMCA in SOI and SOF. This is my eventual goal of my paper. So the data complexity, as we've seen also in the previous presentation, is measured in settings in which we have fixed T box and query, and we only allow the A boxes to be arbitrary. Compare it to the combined complexity from the previous slide, for example, in which all A box, T box, and query are arbitrary. And the data complexity is worth studying because in regular life applications, the query is generally very small, the T box is not as small but still manageable, and the A boxes can be arbitrarily large compared to like the database instant records compared to the database scheme. And the result that I got is that FOMCA is going to be complete with respect to the data complexity in SOI and SOF. There are two main steps to achieve it, achieve this result. The first is that I wanted to prove the so-called linear size countermodel property for SOI and SOF, which means that the smallest finite countermodel for query in these DLs will have size linear with respect to the size of the A box. And I would say that this is the key point of my paper, and it took the most of my work. And the second step, as we already know this property, is quite simple. For FOMCA, we just guess some interpretation, hoping it will be a countermodel, and verify that it is probably indeed a countermodel. And as we know that we can restrict ourselves to countermodels which are of the size up to linear with respect to the size of the A box, the algorithm is QNP with respect to the data complexity, because verification of the properties of a countermodel, it is polynomial in the size of the input interpretation. To obtain this property of linear size countermodels, I need to introduce the notion of a counterexample, which is, roughly speaking, a possibly infinite Forest-like countermodel. And to obtain the small finite countermodels, we start with an arbitrary finite countermodel, which we then unravel into a counterexample, so into this tree-like, forest-like countermodel using the standard procedure. And then we use the properties of the tree automata recognizing the forest of these counterexamples to say that we can pick a regular counterexample. And this regularity is necessary in the next step, which is applying the blocking principle to this counterexample. The blocking principle is a policy in which we want to prune the possibly infinite trees into smaller ones and not trees anymore by descending down different branches, looking for edges which resemble some kind of edges higher up the tree and redirecting them higher up and forgetting the remainder of these branches. So we can apply this blocking principle to, especially to the regular counter examples and not to the any particular one. And my aim, especially here, was to show that the last finite counter model is indeed small. A similar kind of pattern at the pipeline was already present in the paper mentioned before. However, the authors were not concerned with the size of the last finite counter model. They just wanted to show that the existence of a finite counter model is equivalent to the existence of a counter example. And this change required a lot of changes to the details, especially to the construction of the automaton, because previously it was used for two main purposes. First of all, it was used to bound the lengths of simple paths in regular counter examples, which then led to this possibility of applying the blocking principle. Thanks to this regularity, one could technically forget about the transitive roles by replacing a query with some similar query, but still changed a bit, and then work as if the transitive roles do not exist. So the second use of the automata in the previous paper was to verify the entailment in the end by just checking the emptiness of the automaton recognizing counter examples. And the number of its states depended on the ABOX, which had to be changed for my paper because I used this number of states in the final size estimation of the finite counter model, and it popped up in the exponent of the whole expression. So I needed to get rid of this dependency. And also in my case, I used the automata to bound the distances between connected elements in regular counter examples, which allowed me to obtain tighter size estimations. So to conclude, I was able to show the linear size counter model property for SOI and SOF, and also to show that FOMCA is going to be complete with respect to the data complexity in SOI and SOF. And I've shown here the ConnectP algorithm and the ConnectP hardness followed from previous results on this topic, which gave the ConnectP completeness. Thank you for listening. Special thanks go to the supervisor of my master thesis, which is actually this paper, Philip Murlak, for his tremendous help with the whole process, to Poland's National Science Center for providing me with a grant, and also to the reviewers of the year 2020 for their helpful comments and also for giving me an award. Thank you very much.